Have you ever looked at one of those huge apartment buildings and just wondered, how do the lights stay on for everyone, without the whole thing just short-circuiting? Well, today, we're going to pull back the drywall and uncover the hidden rules, the electrical blueprint that powers our world safely.
Okay, so let's really think about this for a second. We're not talking about one kitchen, one TV, or one air conditioner. We're talking about hundreds of them, all drawing power at the same time from the same source. That's the huge electrical challenge of any modern multifamily building. So, how do you design a system that can handle all that safely and reliably without just guessing? Well, it turns out there's a rule book for that.
Right? The answer isn't some wild guess. It's a science, and it's built on decades of real-world experience. It all comes down to this one standardized, universally accepted guide. It's a massive rule book that pretty much every electrician and engineer in the U.S. follows to keep us all safe.
And that rule book is the National Electrical Code, or what everybody in the biz just calls the NEC. Its whole reason for being is to set the standard for safe electrical design. It's there to protect people and property from all the things that can go wrong with electricity. Honestly, it's the reason you can plug in your phone or your toaster without a second thought.
And let's be really clear here, this is not just the list of helpful suggestions. The NEC is the master plan. It is the actual blueprint engineers use to prevent things like dangerous electrical overloads and, of course, the risk of fire. It's truly the foundation of every single safe electrical system in the country. So, how does this blueprint actually work in the real world? Well, it all kicks off with a really crucial calculation. We're about to break down the specific formula the NEC gives us for figuring out the total electrical need, what engineers call the load, for an entire building.
The code makes this complicated problem a lot easier by breaking it into three main categories that we have to add up. You can think of them as the building blocks for our final number. You've got your general power for just everyday stuff, then dedicated circuits for important areas, and finally, you've got the big, power-hungry appliances.
So let's start with general power. The NEC creates a baseline by assigning a standard value for all your general lighting and regular outlets. For every single square foot of living space, the code says you have to account for 3 volt amperes. And don't worry, a volt ampere is just a standard unit of electrical power. It's really similar to a watt. This simple rule just makes sure there's enough juice for all the basics, like lamps and phone chargers.
Next up, we've got to account for the more demanding areas. The NEC sets aside a flat 1500 volt amperes for each small appliance circuit, like the outlets on your kitchen counter, where you plug in the toaster and the blender. Then it adds another 1500 volt amperes just for the laundry circuit, because it knows that a washer and dryer can draw a ton of power. But what about the real power hogs? For the huge appliances like your oven, your clothes dryer, and your water heater, the code gets super precise. Instead of using a general value, engineers have to use the exact power requirement that's listed right on the appliance's own label. That's its nameplate rating. This is to make absolutely sure the system is built to handle their specific, heavy demand.
So you can kind of see the code's clever two-part strategy here. On one hand, you've got these standardized loads, which are just smart estimates for common things that are hard to predict, like how many lamps you're going to plug in. And on the other hand, you have specific loads that use precise, real data for those high-power items you know are going to be there, like an oven. It's this mix of smart guessing and exact numbers that makes the whole calculation work so well.
Okay, but that leaves one giant category we haven't talked about yet. What about the systems that often use the most electricity in a home, especially in the dead of winter or the middle of summer?
Right, so here the code plans for the worst-case scenario, but in a really logical way. Engineers have to calculate the power demand for both the air conditioning system and the electric heating system. And then they just use whichever number is bigger. It makes perfect sense, right? You're never going to be blasting the heat and the AC at the exact same time, so the system only needs to be built to handle one of them at its peak.
So now we have all the pieces of the puzzle. Let's see how they all come together to get that final, super critical number that decides just how big the electrical service for the entire building needs to be. This table really sums it all up perfectly. You take the general lighting load, you add the fixed values for small appliances, then you add the specific ratings for the big appliances, and finally, the HVAC demand. But here's the cool part. You don't just add them all up. The code then applies something called demand factors, which are basically smart adjustments based on the fact that it's super unlikely that everything will be running at full blast at the exact same time. This gives you a realistic final number for the building's total electrical needs.
Okay, I know, that was a lot of calculation. But why does all of this meticulous math matter so much? This is where that technical blueprint connects directly to our safety every single day.
When you get right down to it, the NEC's load calculation is an invisible shield. It's a set of rules working silently in the background, 24/7, to make sure the electrical system inside your walls is designed to be safe right from the very start.
At the end of the day, following this formula is the difference between a reliable electrical system and one that's at constant risk of overload, tripped breakers, or even worse, a fire. This isn't just about convenience. This math is a fundamental piece of public safety.
And that kind of leaves us with one last big question to think about. We're living in an era where we're trying to electrify everything. We've got electric cars charging in the garage, induction stoves in the kitchen, heat pumps replacing furnaces. As our demand for electricity just keeps growing and changing, what's the next great challenge for this code? How is this essential blueprint going to have to evolve to keep powering our future safely? It's definitely something to think about.